Swayam Prabha. Digital India. Educated India.
In the last lecture, we saw the two sample technique of estimation of phasors. We we gave it a test phasor and saw the results of the estimation, and then we added some noise, and then we saw the results of the estimation. We also discussed that in the presence of noise, the two sample technique is not very accurate, though the mean is very close to the value of the phasor. The smear effect is a bit too pronounced. If you compare, then your VM is 10 in the example that we took. This is the result with noise, and without noise we got a very clean kind of result here. This is the result without noise, and this is the result with noise. Now, the reason for this presence of this noise is result for this less accurate result in the presence of noise is the lack of redundancy. What we have here is we have got two measurements and we have got two unknowns. So, the number of measurements divided by the number of unknowns gives us some sort of measure of a redundancy, or let us call it the factor of redundancy, which in this case is 1. It is like me asking somebody the time. Whatever the time he tells me, I have to believe that it is correct. It may or may not be correct, but there is no other method to check. If I ask 2 or 3 people, and then I can come to a correct estimate of the time. Okay. So, what the next logical step here to do is to add some redundancy in the measurement. Before that, let us summarize last time's lecture. What we found is in the presence of noise and the bare minimum number of measurements, which is 2, because we need there are 2 unknowns, the noise will affect the accuracy. How do we filter the noise is what we will see in today's class. Okay. We extend the number of measurements and then see what happens. Okay. So, extending the number of measurement means we need redundant measurements. Okay. So, we defined this redundancy is defined as a ratio of actual number of measurements to the number of unknowns, or the minimum number of measurements. It is the same thing. The minimum number of measurements is equal to the number of unknowns. So, the ratio is the same. Okay. So, now as we said, the next logical step is to increase the number of measurements. So, we increase the number of measurements by how much? By 1 in this case, and then we will see what happens, how to subsequently treat this. So, let us move on to the next part, that is the 3 sample technique. Then we will see, because of the 3 samples, because the number of measurements are more than the number of unknowns, then we will come to a technique known as the least squares technique, or the linear least squares technique in this case. And then we will discuss some aspects of moving windows, and then compare 2 and 3 sample techniques, and then if time permits in today's lecture, we go on to a class of algorithms known as Fourier algorithm. We extend the 3 sample technique further, depending on the time available, of course. Okay. So, again, as we saw in last class and briefly discussed just now, the 2 sample techniques requires the minimum number, or utilizes the minimum number of measurements to estimate the 2 unknowns, that is the VM and phi. or phi v, because we are talking of voltage measurements in this case, then as we saw in any practical system, the presence of noise is inevitable. The instruments are noisy, the communication from the instrument to maybe the relays is noisy. So, presence of noise is inevitable. You cannot eliminate noise completely. Okay, you can minimize it by shielding, etc. But of course, that is not what we are discussing today. But what we are saying is the presence of noise is inevitable. Okay, now the effect of noise, however, we can minimize by increasing the number of measurements, or by, in other words, by increasing the redundancy. So, now after 2 sample, we are going into for a 3 sample technique, in which case the redundancy will be 3 by 2, which is 1.5. Okay. So, now here we extend the number of measurements. We will briefly see this. Last time we had the 2 equations. We will extend that, simply extend that. If you remember last time, that is V1 V2, that is sin omega t1 plus phi, then sin omega t2 plus phi. Similarly, V3 will be sin omega t3 plus phi v. But instead of V1 V2 V3, we will call it, to generalize, so that we can extend it, we will call it Vm sin omega tk plus phi v. Okay. Then the earlier measurement is Vk minus 1 is Vm sin omega tk minus 1 plus phi v, and Vk minus 2 is Vm sin omega tk minus 2 plus phi v. Okay, V1, V2, V3, or any order. So, we have just generalized the equations. The treatment will be similar, but we will see how to go about this. So, similarly, we will expand it. We will write omega theta is equal to theta k, omega tk minus 1 is equal to theta k minus 1, like last time, theta 1, theta 2, theta 3. Okay. So, and we will expand. So, sin a plus b is sin a cos b plus cos a sin b, that kind of expansion, simple trigonometric expansions. Vm sin theta k cos phi v plus Vm cos theta k sin phi v. Okay. Vk minus, similarly Vk minus Vk minus 1 in this case, Vm sin theta k minus 1 cos phi v plus Vm cos theta k minus 1 sin phi v, and Vk minus 2 is Vm sin theta k minus 2 cos phi v plus Vm cos theta k minus 2 sin phi v. Okay. We will write a similar set of matrices like last time. So, we have Vk minus 1, Vk minus 2. These are subscript notations in case, then sin theta k cos theta k sin theta k minus 1 cos theta k minus 1 sin theta k minus 2 cos of theta k minus 2. And the unknowns are the same as last time, Vm cos phi v, Vm sin phi v. Okay. So, now if you notice this matrix, unlike last time where we had a square matrix, this matrix is rectangular. So, it is a, in this case it is a 3 by 2 matrix. Okay. So, inverting it etc., will not be straightforward like last time. So, we have to think of some other method to solve this. Okay. So, let us get back to the presentation. Okay. Okay. So, one more thing is, since we are now talking of noise, the model that we wrote is actually an inexact model, because there is noise. So, there will be some noise term also here. So, we have to be accurate. So, we will have noise here also, which we will represent as Ek minus 1 and Ek minus 2. Okay. So, now let us say call the measurement vector as the B vector. This is the A matrix, okay, which is a constant matrix, and then that is why it is linear least squares, and then this is the vector of unknowns, and this is the noise. Okay. So, you have the form B is equal to Ax plus E. This is the form. Now, we have to find a solution to this. Okay. This, okay, we will see with an example, so that the explanation is more clear. Okay. Okay. So, the matrix form we saw this, that it is written as B is equal to Ax plus E. So, now how do we solve this? It is not a simple matter of inversion of the matrix. If it is B is equal to Ax, we simply x is equal to A inverse of B. So, we do not do that. We will have to solve it by the method of least squares. Okay. So, now to go on to the method of least squares, let us take an example. We will of course come back to our problem of estimation of phasors from the 3 sample technique etc. But to elaborate on the method of least squares, let us just take this example here. It is 3x plus 2x2 is equal to 1, 2x1 plus 3x2 is equal to 3, and 5x1 plus 5x2 is equal to 5. Now, is this system of equations consistent? No, it is not, because if it was consistent, then when you add the first 2 rows, you get 5x1 plus 5x2, but if you add the right hand side, you should have got 4, but in this case you are getting 5. This indicates, in our terms, it indicates some presence of some form of noise. That is why this system of equations you are getting as an inconsistent system of equations. So, if you represent it like we did in this format of Ax is equal to B, then A is a full column rank matrix, then system of equations will be consistent only if the rank of A is equal to rank of A comma B, and that is the augmented system. So, if 5x if the last equation was 5x1 plus 5x2 is equal to 4, then the rank of A here in this case is 2, because of course the maximum rank can be 2, because the number of columns here is 2, though the number of rows is 3. So, the third equation is redundant in this case. But when you augment it, it becomes 3 2 1 2 3 3 and 5 5. If it was 4, then it would become 5 5 4, in which case the last row would be linearly dependent on the other 2. So, the rank of that also would be 2. So, in the system of equations would be consistent only rank of A is equal to rank of A comma B. Now, since that is not the case here, since the rank of A is 2 and that is the number of linearly independent columns here is 2, and rank of AB, which is a square matrix where the rank, of course, the rank, the number of whether you call it the column rank or row rank, it would be the same, but in this case the rank of A comma B is 3. So, the system of equations is not consistent. Okay. So, now we can say that the inconsistency, as we mentioned earlier, is there due to the presence of some noise. Okay. So, now we have to somehow eliminate this noise. Okay. But to eliminate it, we have to get to an estimate of the noise and then eliminate it. Okay. So, you cannot do it in the frame of the linear system of equations where you had number of unknowns equal to the number of measurements and the equations were consistent. You cannot solve it in that framework. Okay. So, now we use the method of least squares for this. Okay. So, our aim is to find a vector such that Ax is closest to B. Okay. We cannot make Ax equal to B because in which case the system would be consistent and that means B would lie in the range space of A. That is not the case here. So, or the column space of A, but that is not the case here. So, we find a vector or we define a vector which is R, in which case we define it as R is equal to B minus Ax. Okay. And then we minimize the Euclidean length of this R. Now, what is the our second norm? We could do it on the first norm also, in which case it is known as the least absolute value, not the least squares. Okay. So, if the components of R are R1, R2, etc., Rn, then what we try to do is we minimize the R1 square plus R2 square up to Rn square. Okay. So, this is what we minimize and then we come as close to Ax as possible with our estimate of B. Now, the thing is, can we make it 0? That is not in our hands because we do not know, we can't eliminate noise. Okay. What we can do is we can try to make it as close to 0 as possible. So, that is what we are trying to do here and that is what we are trying to optimize. Okay. So, what we are doing is the Euclidean length in vector terms is also given by R transpose R. So, R transpose R is, so we are trying to minimize that. Actually, this squared, we are trying to avoid the use of square roots, etc. So, we minimize R transpose R. Actually, we minimize half of R transpose R. This half is just a scalar multiple because it is a quadratic expression. When you take derivatives, you will get a 2. Just to eliminate that, we use half. We could as well work with R transpose R. I mean, that is just a multiplier used for our convenience. Okay. So, here the vector square root of that represents, as we said, represents the closeness of Ax to B. Okay. So, we define a function phi x which is half of R transpose R and we try to minimize that phi x here. Okay. So, since R is B minus Ax in matrix terms. So, half R transpose R becomes B minus Ax transpose B minus Ax. Okay. So, if you expand it out in matrix terms, you will get half of X transpose A transpose X minus B transpose Ax plus B transpose B. Okay. So, now we let us from our problem earlier, let us try to evaluate this. We have it here. I will just. Okay. So, how did we come to this? I will just will write that and quickly we will not actually do the actual differentiation, but I will just show you how we came to our system of equations was 3 2 1 and 2 3 3 and 5 5 5. And now we have to, or 5x is half of x transpose A transpose Ax B transpose B. Okay, I think this is minus. Okay, so now we have to, what is A transpose A? Okay, so now A here in this case is 3 2, I am sorry, 3 2 2 3 5 5 and x 1 x 2 1 3 5. So, what is A transpose A? This is A this is X, this is B. So, A transpose A will be so, we have 9 plus 4 plus 25, so 38. Okay, then you have 6 plus 25, so 37. Okay, and similarly 6 plus 35, 37, and 38. So, A transpose A is this. What is B transpose? B transpose A, B transpose A is 135 B transpose A. Three plus 6 plus 25, that is 34, and 2 plus 9, 11 plus 25, 36. Okay, that is B transpose A, and B transpose B is again 135. One plus 9 plus 25, so 35. Okay, so this is what we have got here, and then we will have to. Okay, so to find the minimum, what do? We will differentiate. Of course, we have just expanded this. X transpose is x1, x2, and x is of course x1, x2. Then we have expanded this, and this is what phi x looks like. And to find the minimum, we will first differentiate phi x with respect to x1 and set it to 0, and then differentiate phi x2, differentiate phi x with respect to x2, and then set it to 0. So, what we get is these two set of equations. You can do it for yourself and see. It is quite simple, and then this results in the optimal solution. X1 is equal to minus 5.33 and x2 is equal to 1.466 n. If you are, you can do it as well on MATLAB or Octave and see it for yourself also. Okay. So, now having seen it with an example, let us get back to our problem of estimation of phasors. So, we will look for some generalized solution. So, our system of equations given by is represented in matrix form by B is equal to Ax plus E, where E represents the noise. Okay. A is the constant matrix here, which consists of the sin thetas and cos thetas, and B is the measurement vector. X is our Vm cos phi and Vm sin phi. Okay. So, but in general, if we want to discuss the theory of least squares, we can proceed on this lines only. B is here is m into 1, that is the measurement vector, and A is the you can call it the state matrix here in m cross n matrix. M is the number of measurements, which in this case will be more than the number of equal to or more than the number of unknowns, which is n. Okay. So, in other words, no, number of unknowns is less than the number of knowns, equal to or less than. Okay. So, we define a function phi x as B minus Ax transpose B minus Ax. Okay. So, the in vector terms we instead of differentiating with respect to x1 and x2, we have taken the gradient of this function here, and A transpose the gradient of the function is given by A transpose Ax minus A transpose B. Now, we have to set this gradient to 0 for the minimality condition. Okay. So, here if you see if A is full column rank, then A transpose A will be a positive definite matrix. That means all the eigenvalues will be strictly greater than 0. Okay. So, and in the plane of the eigenvalues, if the curvature is positive, okay, the gradient is 0 and the curvature is positive, then you have got a minimal point. Okay. If the curvature is, if the gradient is 0 and the gradient is negative, then you have come to a maxima. Okay. The full column rank or the positive definite of A transpose A guarantees that the solution is not only exists but is unique. Okay. With a quadratic function like this, you will get a solution even if A is not full column rank, that is some of the eigenvalues are 0 or A transpose A is a positive semi-definite matrix. So, you will get solution, but you do not know whether the gradient is 0, but the curvature may be positive or negative. So, there may be solutions, but there may be multiple solutions. Okay. You will not have a guarantee of a unique solution, which in our case is is very much if I were to use the term useless, because you can't have the phasor, say let us talk about the magnitude only in this case, the phasor magnitude could be 10 or 15 or 25. No, it will not solve our problem at all. But fortunately for us, we will not encounter such problems in, at least in our power system problems. Okay. So, now we have to solve this system here, A transpose A is equal to A transpose B, because we have set this gradient to 0. So, now what is A transpose A in our case? If you remember, this is our A matrix here. So, A transpose A will be the first term will be sin theta k into sin theta k plus sin theta k minus 1 into sin theta k minus 1 plus sin theta k minus 2 into sin theta k minus 2. So, it will be a summation of sin square theta k's, okay, k ranging from k minus 2 to k. Then the second term will be sin theta k cos theta k plus sin theta k minus 1 cos theta k minus 1 plus sin theta k minus 2 cos theta k minus. So, it will be a summation of sin theta cos theta k's. Similarly, the 2,1 term will be cos theta k sin theta k plus cos theta k minus 1 sin theta k minus 1 plus cos theta k minus 2 sin theta k minus 2. So, similar to the 1,2 term here. So, summation of sin theta cos theta, and the last 2,2 term will be cos theta k into cos theta k minus 1 into cos theta k minus 1 and cos theta k minus 2 into cos theta. So, it will be a summation of cos a square theta k's. Okay. And the A transpose B term similarly will be given by it will be similar combination of, or the dot product of the measurements into either sin theta k or cos theta k. Okay. So, this is our A transpose A. This is our vector of unknowns x, that is Vm cos phi v and Vm sin v, which is represented as Vj's here, and then we have B. I am sorry, which is not Vj's here. Vj's are the measurements here, Vk minus 1, Vk minus 2, Vk, and I am sorry, the Vj's are Vk minus 2, Vk minus 1 and Vk. Okay. So, this is A transpose B. Okay. So, now instead of doing the inversion, we will use a small I would not say a trick, but we will use a small manipulation. What do we have here in the first term? Now, we will now have to okay. So, what we will do here is we will have to that kind of manipulation we will not be able to apply here. So, what we will do here is we will invert this matrix and then find the solution to the Vm cos phi b and Vm sin phi b, like we did last time. But what we have to keep in mind that this matrix inversion will be involved at every step of the phasor estimation. Okay. So, though we have added a bit of redundancy here by increasing the number of measurements, we have also added a little bit of complexity in the computation. Okay. But the results will justify that. Let us see, if we give our same signal here, V is equal to Vt is equal to 10 sin 2 pi ft plus 30 plus plus the noise that we have added E plus random, like similar to last time. The sampling time is 5 milliseconds. So, we have got 4 samples per cycle, and first is a 2 sample technique, and on the right hand side of the table is the results from the 3 sample technique. So, if you observe here the same thing is your 100 samples and taking the mean and standard deviation, etc. So, if you observe here that as the noise increases, if you take the worst case where your E is equal to 3, the maximum noise that we have simulated here, then what happens is we saw that the mean here has, we saw this last time also, that the mean has now gone significantly away from 10, and it is 11.4, and the standard deviation, the spread is also much more, is 4.38. However, with the 3 sample technique you get 10.5, and even the standard deviation is much lower. So, you can see that the 3 sample technique here is far superior. You get much better results as compared to the 2 sample technique. That is for the simple reason that we have added redundancy. Okay. Of course, that involves a bit more of complexity, because you have the sin cos multiplication also, but the results justify that. Okay. So, we will just sum up what we have done. That the 2 sample technique does not have any kind of redundancy, while the 3 sample technique has a redundancy of 1.5. Okay. And because we have added redundancy, the results are also better. Now, the next logical question to ask is, if 3 sample is better, then how much do we increase the number of sample? Okay. So, the answer to that is, people have gone for 12 samples, 16 samples, 20 samples is by far for the commercial available relays. That is around the number sampling that is used. 12 samples will actually give you the advantage that you have 2 pi by 12 theta. So, that pi by 6, so you have multiples of 30. So, your computation becomes easier. Okay. With 4 and if your processor is very you have olden times of processors where your processor speed is very slow, then you can even go for though that is no longer the case with modern processors, but you can go for 4 sample if your processor is very slow, you are doing it in a lab or something. Then with 4 sample you have pi by 4. So, I am sorry, pi by 2, so 90 degrees, so plus minus 1, so you are only dealing with plus 1 minus 1 there. So, your computation becomes very simple. Okay. So, as long as the number of samples is more than 2, and then for redundancy more than 3. So, commercially available samples or sampling rates rather will be 12 samples or 16, 20, that range. Okay. So, now we will go on to another class of algorithms for phasor estimation, which is the Fourier or Fourier-like algorithms. Okay. So, here in this case we will discuss the full cycle Fourier algorithms. We will discuss the equations pertaining the same. We will look at the trying to speed this up. We will discuss the reasons for that. Then we will look at half cycle Fourier algorithms, and then maybe in the next class we will look at how to eliminate DC offset using things like mimic impedance, etc. Okay. So, now till now with 2 sample and 3 sample we have our data window was characterized by the number of samples. So, if delta t was our sampling interval, then with 2 sample our our data window length was delta t, and with 3 samples it will be 2 delta t. Okay. So, there is another method, another way of looking at the sampling window, which can be a full cycle. Okay. We can also have half cycle, which we will come to a little later. So, irrespective of the number of samples, as long as the number of samples is greater than 2 to satisfy our Nyquist criteria, irrespective of the number of cycles, our data window length will span a full cycle. So, if it is a 50 Hz system, then it will be T naught or 20 milliseconds. Okay. So, you may have anything more than 2. So, 3, 4, 12 as we discussed, 16, 20 samples in that window length. Okay. What advantages that gives us, we will see using a full window length, full cycle window length. Okay. So, this our system of equations is the same. Okay. Only in this case, let us say there are k samples per cycle instead of we talked of 3 and 2 earlier. So, let us say there are k samples per cycle starting from the index we have started from 0. So, from 0 to k minus 1. If you start the index from 1, it will be sin theta 1 to sin theta k. But since we have started it for 0 for convenience, our k samples will span from what t0 to tk minus 1, and correspondingly they will be sin theta 0 to sin theta k minus 1. Very similar to the 3 sample technique here. Okay. So, the matrices look same, only the number of measurements and the number of is equal to, in this case, k. So, that has increased. It could be 3, but then we are talking in a general sense of k measurements here. Okay. So, similar to that sin square theta j, the A transpose A matrix will give you an addition of sin squares in the 1 comma 1, an addition of cos squares in the 2 comma 2 here, entry here, and a summation of sines and coses in 1 comma 2 and 2 comma 1. Okay. And similarly, the A transpose B will be a dot product of the measurements and sin theta j and cos theta j. Okay. So, let's see some unique property here. Okay. So, what was our signal? It was, say, Vt is equal to Vm sin of omega t plus phi v or phi for convenience, let us keep it as phi. Okay. So, now let us call this the associated term with cos phi as Vc, and this let us call it as Vs. Okay. So, what do we have? We have Vt is equal to Vc, I am sorry, this it is the other way around. Let us write it for convenience sake as so, this we call Vs and this we call Vc. The term associated with sin omega t we call Vs, and the term associated with cos omega t we call it Vc, which is what we have to estimate, Vs and Vc. Okay. So, Vt is equal to Vs sin omega t plus Vc cos of omega t. Okay. So, now to estimate Vs, we need to get rid of this term. Okay. So, what we will do is we will employ a small trick here. What we will do is we will say Vs sin square omega t, we are multiplying it by sin omega t plus Vc cos omega t sin omega t is equal to Vt sin omega t. Okay. Now, this term still there. So, we need to sort of get rid of it. What we will do it, we will integrate it from, if the time period is t, then we will integrate this whole thing from sin square 0 to t dt plus 0 to t Vc cos of omega t sin or sin omega t cos omega t dt is equal to 0 to t Vt sin omega t dt. Okay, now what is sin omega t cos omega t? 2 sin a sin b is sin 2a by 2. Okay, so what we get here is, this also we will do it, but later. Okay, so what is integral of sin 2 omega t over the time period t? T is the full cycle. So, what you have? This is a double frequency over a time period t. Okay. So, what is the average value or what is the area here? It will be 0. Okay. So, this term goes to 0. Sin square omega t also you can write as 1 minus cos 2 omega t by 2. The second term is a again a double frequency term that will get killed. Sin square omega t is 1 minus sorry. So, this term will again go to 0, the second term. What will remain is half, and integral of Vs dt, Vs is a constant for over t. So, integral of that will give you t by 2 into Vs is equal to 0 to t Vt sin of omega t dt, or Vs is equal to 2 by t 0 to t Vt sin of omega t dt. Similarly, if you can do it for for cos, if you want to estimate Vc, then you multiply it by cosine, then this term will become sin omega t cos omega t, the first term will go. So, the second term is cos square omega t, which is cos 1 plus cos 2 omega t by 2. So, that will similarly give you a result of Vc is equal to 2 by t 0 to t Vt cos of omega t dt. So, this is for those who are familiar, this is your orthogonal projection of your signal on sin omega t cos omega t, similar to your Fourier algorithms. Okay. So, if you discretize this, what you will get is Vs, you can do it for yourself and see, you can do this by the trapezoidal rules of integration 0 to k Vk sin of 2 pi k, and whatever this index is. If suppose you take this index as, since I have taken it as k, this is small k, this is large k. K is the number of samples, or if you take it as n, then number of samples per cycle. Okay. So, and Vc is equal to, which is what we have got from the method of least squares. Okay. I have just used the integral, the continuous function here instead of the discrete, because it is easier to explain, but you will get the same result in any case if you were to use that method also. Okay. So, let us get back to the presentation here. So, this is your sin square t terms. These terms will the off diagonal terms will go away, you will get 0, and here you will get k by 2 k by 2. Now, not only is this matrix a constant, okay, it is also a diagonal matrix. So, your problem of inversion at every step is no longer there. Actually, it is just a trivial problem now. Okay. So, this is what we derived Vm cos Vm cos phi v is this and Vm sin phi v is this part. Okay. So, this is what we just derived, but in the integral form. Okay. So, this is the Fourier algorithm here. Now, this is what we solved here. Okay. So, we just showed that the off diagonal terms, how they are I mean we solved a similar problem, but we solved it directly here, but this in a sense explains how the diagonal terms come to be k by 2 and the off diagonal terms are 0. Okay. So, this is the notation that we use. Vs is equal to Vm cos phi v and Vc is equal to Vm sin phi v. In case there is an interchange of notation, you will get the similar set of results here. Okay. So, now okay. So, now coming to it, that what the calculations that we did were for the first window, okay, the first k samples. We will now have to generalize it for say the nth window, means because this is a moving window calculation, you do not do the calculation once and forget about it. The window, though it is a one cycle window, it keeps on moving. So, one sample goes in, the latest sample comes in, the oldest sample goes out. Okay. So, continuing in that fashion, the window number is the number of the latest sample. Okay. So, to generalize that to, if it is the nth sample, then it has to go from because we have got k k samples here. So, it has to go from L minus k plus 1, because there we it was earlier going from 0 to k minus 1. So, now the upper index is L. So, the lower index obviously has to be L minus k plus 1 to maintain the same number of samples in that window. Okay. So, you just change the indices here, just manipulated the indices for j is equal to L minus k plus 1 to L, and the rest of the treatment remains the same. So, if you noticed, and for those of you who have done DFT discrete Fourier transforms before, this set of equations is identical to the DFT equations. We will see DFT in greater detail. The only change could be the constant could be different, that 2 by k, because it is anyway a scalar multiplier, it could be root 2 by k or anything. So, we will see that you could choose it in any fashion as long as the it is consistent between the Fourier transform and I am sorry, the discrete Fourier transform and the inverse discrete Fourier transform. Okay. So, let us having got this, let us see what are the results obtained from the full cycle Fourier algorithm. Now, to compare, we have taken the 2 sample algorithm, the 3 sample algorithm, and a full cycle Fourier algorithm with number of samples equal to 10. Okay. So, so as we expect, as we increase the number of samples, we have also increased the window length of a full cycle. We would expect an increase in accuracy, and you can see that for our earlier example of maximum noise, the same thing is done 100 samples and then calculate over over that same windows. So, and the noise is increased progressively. So, for a maximum E of 3, then that is the maximum level of noise. For a 2-point algorithm, we see that this is the same result as earlier, 11.4, that is the mean. Remember that the value of Vm is 10, okay, and the standard deviation is 4. So, wide oscillation, if you can call it. Then for the 3-point algorithm, the mu is 10.5 and sigma is 2.76, and for the full cycle Fourier with 10 samples. We could also repeat this experiment with and see what happens if you make the sample 16 or 20, what gain in accuracy is there, but we have used 10 here. So, again mu goes to 10.24, and even the standard deviation is far lower. So, you can see that as you can expect, as you increase the number of measurements, the results are far better. Okay. Again, this is as expected from the theory that we developed. Okay. So, this we saw that sigma is the mean actually here. So, we have got far improved accuracy here from this is close to 10, quite close to 10 as compared to say this, meaning 10.24 as compared to 11.4 or even 10.54. Okay. So, greater accuracy, but of course, the trade off is there will be longer time in between required for the computations. Okay. For 2 and 3 sample algorithms, after the I mean you require just the either the delta t or 2 delta t before you do all your phasor computations, but in this case you will require one full cycle. You will have to wait for one full cycle, and your all your algorithms that we discussed earlier, overcurrent, distance, differential, all that will have to the computation will have to wait for one full cycle. Okay. And we will see how that is a problem and what can be done to address that. Okay. But before that we will also see some more, since we are now this is some sort of a digital filter. We are filtering out the phasor or the fundamental component of that. So, let us see the filtering capability of the full cycle algorithm. We will also then have a comparative look at the filtering capabilities of all the algorithms, maybe in the next class. So, this is a square periodic wave. The amplitude is 10 here. You can see in the waveform that is there in the figure. You are aware that a square wave will have odd harmonics, the first, the fundamental component, the third, fifth, seventh, and so on and so forth. Okay. So, let us have a look at the harmonic rejection capabilities now. We expect that the true value of the fundamental is 4 pi by 10. We know this from our earlier theory, that the fundamental component is 12.73, okay, or 4 by pi into 10, 12.7324. Then the frequency is 50 hertz, and we have taken 10 samples per cycle, same as the earlier case. Okay. And some noise is added. Okay. If there was no noise, you would have seen that the mean is exactly 12.7324, but now some noise is added, and the same experiment as earlier is repeated. You same 100 estimations and then find the mean and standard deviation, etc. over that. So, if your noise is very small, it is quite close to 12.73. You can see that the mean is close to that, and as you progressively increase the noise, the mean also is deviates from that 12.73, but it is still okay, quite close to 12.73, and even the spread or the standard deviation is quite okay. Okay. So, we can conclude that the full cycle algorithm gives a good accuracy. Okay. Now, we were here, so we conclude that the accuracy obtained is quite okay. Now, as we said, we all our computations, etc., that need to be done, like distance or even overcurrent, they have to be done, or they have to wait for the phasor estimation to be complete. Okay. So, we have to wait one full cycle for it to be complete, and where very fast relaying decisions are involved, there are needed, rather not are involved, are needed. Can we do something to reduce this time as much as possible, but not and we will see what the trade off is in terms of the accuracy. So, now earlier in the earlier example, we did this, right. We took our same, we'll do the same thing. Vt is equal to Vm sine of omega t plus phi. So, Vt is equal to Vm sine omega t cos phi by Vm cos omega t sin phi. Okay, so Vc, I am sorry, the same mistake again. Okay. So, what do we have? Vt is equal to Vs sin omega t plus Vc cos of omega t. We will do the same kind of projection here. First, we will do it with okay. Now, oh, this is missed. Okay. Now, instead of integrating from over the full time period, we will use some arbitrary time period tau. Okay. So, what we do is 0 to tau Vt sin omega t dt is equal to 0 to tau Vs sin square omega t dt plus 0 to tau Vc sin omega t cos omega t dt. Okay. Now, it's same thing again here. We will get sin omega t cos omega t will become sin 2 omega t by 2. So, what we have is 0 to tau Vc sin 2 omega t by 2 dt. Now, if this term has to go to 0, if you have let us see, you have a double frequency term, okay, and this is your time period t. Okay. This is a double frequency term. So, even if you take t by 2 instead of t, you take this time period is t by 2. Okay. The area under the curve or the integral is still 0. So, this will be 0 for t is equal for tau is equal to t by 2 also. It will be 0 of course for tau is equal to t, tau is equal to 2t, tau is equal to 4t etc. or 3t, 4t etc. So, we will stop here and continue next time.